Section 9.4, Singular Value Decomposition. Let's start with the theorem. If A is an n by n matrix, then A and A transpose A have the same null space, A and A transpose A have the same row space, A transpose and A transpose A have the same column space, and A transpose A have the same rank. Also, if A is an n by n matrix, then A transpose A is orthogonally diagonalizable, and the eigenvalues of A transpose A are non-negative real numbers. Let's prove that theorem right now. So first of all, the matrix A transpose A is symmetric, so that automatically makes it orthogonally diagonalizable. Then, since A transpose A is orthogonally diagonalizable, there is an orthonormal basis for Rn consisting of eigenvectors of A transpose A, let's say v1 through vn. If we let lambda 1 through lambda n be the corresponding eigenvalues, then for I between 1 and n, we have that the length of AVI squared is AVI dot AVI, which is VI dot A transpose A VI, right? We can move the A in by writing A transpose. That's the same thing as VI dot lambda I VI, because A transpose A is lambda I. So then we have the lambda I factoring out. So we have lambda I times VI dot VI, which is lambda I times the length of VI squared, and that's 1 because the base is orthonormal, so we just have lambda I. So that means that we have that the lambda I must be greater than or equal to 0 because it's equal to the length squared. If A is an n by n matrix, and if lambda 1 through lambda n are the eigenvalues of A transpose A, and remember now we know they're non-negative real numbers, then the numbers sigma 1, sigma 2, etc., where they're all the square roots of the eigenvalues, are called the singular values of A. Let's find the singular values of this matrix right over here. So first, let's write out A transpose A. So that's equal to 1, 0, 1, 1, 1, 0, times A is 1, 1, 0, 1, 1, 0. And we get 2, 1, 1, 2 when we do the multiplication. So now we can write out the polynomial, characteristic polynomial, lambda squared minus 4 lambda plus 3, which factors as lambda minus 3 times lambda minus 1, and so we get eigenvalue of lambda 1 equals 3 and lambda 2 equals 1. So then our singular values are the square roots of those guys, so the square root of lambda 1, so that's the square root of 3, and our other singular value, sigma 2, is the square root of lambda 2, which is 1. We define the main diagonal of an n by n matrix to be the line of entries shown in the figure. This line right over here. It starts in the upper left corner and extends diagonally as far as it can go, so it might not cut through the entire matrix. We will refer to the entries in the main diagonal as diagonal entries. Let's talk about singular value decomposition now. If A is an n by n matrix K of rank K, then A can be expressed in the form A equals U sigma V transpose, where sigma has size m by n and can be expressed in partition formed as a diagonal matrix and a whole bunch of zero matrices. So D is a diagonal K by K matrix whose successive entries are the first K singular values of A in non-increasing order. U is an n by n orthogonal matrix, and V is an n by n orthogonal matrix. Turns out, singular value decomposition is another kind of way that we can decompose matrices to solve linear equations more easily. Computers really like using this kind of form, and it's kind of analogous to the other forms that we decompose matrices in section 7.2. It has an expanded form where we more explicitly write out what's going on. We have U sigma V transpose, so this is the matrix U. This is the matrix sigma. Here we have all of the singular values along this shorthand D, and then these are all just zero matrices. and we multiply by V transpose. So that's why we get this vertical matrix right over there. So V equals V1 through Vn orthogonally diagonalizes A transpose A. Non-zero diagonal entries of sigma are those singular values we talked about. And the column vectors of V ordered so that the singular values start decreasing, or they're in decreasing order. And the U's are given by AVI divided by its length. It's the same as 1 over the singular value times AVI. U1 through UK is an orthogonal basis for the column space of A, and U1 through UM is an extension of U1 through UK to an orthogonal basis for Rm. Let's do an example where we find a singular value decomposition of the matrix we were looking at before. So remember that we said that A transpose A was equal to 2, 1, 1, 2. So we also had that lambda 1 was 3, lambda 2 was 1, which gave us singular values of square root of 3, and square root of 1 is 1. So let's look at our first eigenvalue, lambda 1 equals 3, and let's get a corresponding eigenvector. So we'll take lambda I minus a, plug in 3 for lambda, and we'll get 1, minus 1, 0, minus 1, 1, 0 by setting it equal to 0. Reducing this, we get 1, minus 1, 0, 0, 0, 0. So that gives us a top equation of x1 minus x2 equals 0. We have x equal to t times 1, 1. Because this means that x1 equals x2, we can set both equal to t, factor out the t. In any case, we'll get that a vector is 1, 1, and we can normalize it to get an normalized vector so we can get an orthogonal basis. So we'll get v1, when we normalize 1, 1, by dividing by its length, we get square root of 2 over 2 and square root of 2 over 2. Let's do the same thing now for lambda 2. So that's 1. So plugging in lambda equals 1 into lambda I minus a, we get minus 1, minus 1, minus 1, minus 1, set that equal to 0, 0, and reduce, and we get 1, 1, 0, 0, 0, 0. So our top equation now is x1 plus x2 equals 0. So that means that our vector x, we could factor out t, get 1 minus 1, because x1 is minus x2, and by normalizing that, we'll get our second vector for our orthogonal basis, square root of 2 over 2 minus square root of 2 over 2. So now let's figure out what u1 is. So u1 is given by 1 over sigma 1 a v1, right? That's how we're getting u1. It's av1 divided by length of av1. So that's square root of 3 over 3 times a is 1, 1, 0, 1, 1, 0. And then v1 is square root of 2 over 2, square root of 2 over 2, giving us square root of 6 over 3, square root of 6 over 6, square root of 6 over 6. Okay, let's get u2 now. We'll do the same thing, except now it's 1 over sigma 2 for the other singular value, av2. So 1 over 1 is 1. And then a, again, 1, 1, 0, 1, 1, 0. And we multiply by square root of 2 over 2 minus square root of 2 over 2. So So this gives us 0 minus rad 2 over 2, rad 2 over 2. So now we'll take square root of 6 times u1, so that way we can get rid of these square roots, get a nicer form for u1. So we'll get 2, 1, 1 by multiplying through by rad 6. And let's how about multiply this guy by rad 2, and we'll see that rad 2, u2, is equal to 0 minus 1, 1, because these forms of u1 and u2 will be easier to work with. So now we'll take 2, 1, 1, 0, minus 1, 1, times x1, x2, x3, and set that equal to 0 so that we can solve for x. This x is exactly what we need to extend our basis of u's, because remember that the capital U that we have is not just the u's, the u1 through uk's. Right now we have the u1 through u2. For this part, we also need to extend it to, in this case, R3. Right, that's our last step, because we have the orthonormal basis for the column vectors of A, but we don't have the extension yet. So we'll find that missing third vector, and we'll do that by solving for 2, 1, 1, 0, 0, minus 1, 1, 0. Remember, this is u1, and this is u2. Reducing this, we get 1 half, half, 0, 0, 1, minus 1, 0, which reduces 2, 1, 0, 1, 0 by subtracting half the second row, and 0, 1, minus 1, 0. So that top row gives us x1 plus x3 equals 0, and the second one gives us x2 minus x3 equals 0. So therefore we can set x1, x2, x3 equal to t times, we'll make x3 t, so then x1 is minus t, so we have minus 1, 1, 1. We factor out t, which gives us a u3 of minus 1 over rad 3, 1 over rad 3, 1 over rad 3 after we normalize. Okay, so now we can write out our singular value decomposition. First we have to start with A, which is 1, 1, 0, 1, 1, 0, so that was the A we started with, and we need that to be equal to some u. We can't use the modified u's because they are not normalized. We have to use the original u's, but when we had them normalized before messing with them, we only multiplied by rad 6 and rad 2, so it would be easier to find that u3 because we could always normalize it later. But returning to the to the originally normalized, we will take square root of 6 over 3, square root of 6 over 6, and square root of 6 over 6. So that's our u1, and then u2 is 0 minus rad 2 over 2, rad 2 over 2. That's what we got when we normalized. And then our last u3 vector is 1 over rad 3, 1 over rad 3, 1 over rad 3. So this is u. And then we multiply by sigma, which is built out of the singular values. So that was square root of 3 and 1 on the main diagonal, because square root of 1 is 1, and then zeros otherwise. Okay, and now we just need V transpose. So V was square root of 2 over 2, and square root of 2 over 2, square root of 2 over 2, and minus square root of 2 over 2. That'll be V transposed. And there's our singular value decomposition of A.